Welcome to the HPC Best Practices webinar series, which is brought to you by the IDEAS Productivity Project, funded by the Exascale Computing Project, in collaboration with the U.S. Department of Energy, computing facilities at the Argonne Oak Ridge and Lawrence Berkeley National Laboratories. I'm Osni Marquez with Lawrence Berkeley, and Ashley Barker and I will be the hosts for today's webinar, Containers in HPC. The webinar will be presented by Shane Cannon, who is with Lawrence Berkeley and NERSC, National Energy Research Scientific Computing Center. He's a senior engineer here at NERSC, and where he works in the supercomputing facility. Over Shane's 20-year career, he has focused on enabling scientists to conduct breakthrough sciences using large-scale systems, including some of the fastest computers and storage systems in the world. Most recently, he has focused on enabling data-intensive computing, container computing, and supercomputing systems. And Shane is also a senior member of the DOE Knowledge Base, or K-Base project, which is building a platform to conduct biological research that can be easily shared with reproduced. And he has a PhD in physics from Duke University. With that, Shane, please.
All right, I'll take over. You want to unshare, and I'll try to.
I've made you the presenter, Shane. You're good to go.
Okay. All right. Good. And let me just go full screen here. Give it a second to flip over. Okay, great. Hopefully everybody looks like the right thing's showing up. So thank you, Osni, for the introduction, and thank you also for the invitation from the IDEAS team. I'm sort of consider myself an evangelist for container computing, especially in sort of high-performance computing and scientific computing. So I always welcome the chance to tell more people about it and reach a broader audience. So this is a great opportunity. All right, just briefly, here's what I'm hoping to cover during today's session. I'm going to give you a little bit about what containers are and why they might be of use to you, especially those in the sort of scientific and technical computing community. I'm going to give a very basic sort of demo of sort of Docker kind of basics, just to familiarize you with some of the concepts. I'm going to talk about containers in HPC, and I'm one of the developers of a tool called Shifter, so I'll center on that at first, but then I'll also follow on with some discussion about other HPC container runtimes that people may be familiar with and you could also use in similar ways. And I'll talk a little bit about tips and tricks and then finish with a summary. And here's a GitHub repo that you can go and access that has some of the materials, especially some of the sort of hands-on stuff. So even if you don't get through it today, you can go and try to follow through that on your own at home. Okay, so let's talk a little bit about like what some of the issues that containers can help address. So I'm at NERSC, which is a supercomputing center that supports thousands of users, and these are some of the questions and sort of complaints that we sometimes hear. So my software doesn't build on the system. I'm missing dependencies. There's libraries missing. I need version 1.x of this tool, but your system has a different one. Can you do something about it? There is some complaints about no sound, but I think, Ashley, you are hearing me, correct?
I am. I think most people can hear. I'm working with a couple of people who are having issues.
Okay, good. I didn't want to forge along and nobody's hearing me. I need to kind of reproduce this same application or same run in 12 months from now. I want to get the same exact things on another system, or even I want my collaborators to be able to run the same tools, and I don't want to worry about like there's something different with their environment that interferes with things. And then, finally, people may have actually heard about containers and start to ask directly about them. Like, I've heard about containers, I've heard about Docker, can I run that? In fact, we get people that say, like, I'm trying to run Docker on this system and it's not working. So, this is where containers can play a role. So I'll talk about a little bit about why, but first a little bit of background about containers. So really when we talk about containers, it's kind of a combination of capabilities that are already in the Linux kernel, mainly C groups and namespaces that you can use to kind of create these isolated environments. So, it's similar in some ways to virtual machines, but it's a little bit lighter weight, and I'll talk about some of those differences later. And while there's, it's been all the buzz over the last, 3 or 4 years, it's actually had a long history. So there was kind of forms of containers even in Solaris a long time ago, back in 2005. And the early sort of foundational pieces for containers really goes back to like 2008. And what really changed over the last 4 or 5 years is with the advent of Docker, you suddenly had a tool that really lowered the barrier and made it easier to kind of use this capability. And it created sort of the full sort of end-to-end tool chain that you needed to kind of build these things and run them at different places. And from that, what we've seen is just this sort of entire ecosystem kind of explode around containers. And so, you may hear about Docker, but you may also hear about things like Kubernetes and some of these other orchestration pieces. A lot of these are kind of outgrowths of what was initially started with the container movement. So at its foundation, what containers allow you to do is kind of the way we talk about it is build, ship, and run. So it gives you tools to and a model for like being able to create a recipe of how you want to construct this environment, this image, build that, ship it by pushing it to a repository called like Docker Hub, which if you use Git, it's kind of the same thing, but for containers. And from that, it makes it easy to share those and then run it. So pull those images down and use a Docker engine or some other runtime to execute those images and create a containerized environment to run your application or service or whatever, right? So again, what Docker really did that was revolutionary is it provided kind of this end-to-end solution to make this process easier. Before that, it was pretty clunky. Why is this interesting to scientists and some technical computing spaces? A couple of things that I like to hit on. One is productivity. So, if you've ever been in this case where like I can install this stuff on my system, my personal system, but when I try to go to another place, it's really hard. Or, I'm trying to run code at a center and it doesn't have the right pieces, dependencies for me. Now all of a sudden you can kind of solve all of those things yourself. Reusability and collaboration, and this kind of goes hand in hand with productivity. Now you can start to build something, and rather it just be for you, you can easily share that with collaborators, for example, or even make it part of a publication so it's more reproducible. So now when somebody sees your analysis, they can even pull down that exact image that was used to do the analysis and sort of repeat it for themselves or repeat it on a different data set. And then lastly, it provides this layer of portability. So I can build something on, say, my laptop and then go run it on an HPC system using some of these HPC runtimes, or run it in a cloud environment or other centers, with the one caveat that these do have to be of the same sort of architectural family. So it's not a panacea, but it certainly lowers the bar. If you're kind of operating in the x86 kind of space, it's pretty powerful. All right, so that's just a quick intro to what containers are and why they're awesome for science. Let me now switch over, and I'm going to briefly stop the slides, and I'm going to switch over to here. So this is, let me just, maybe before, is there any quick questions that we want to? Okay, there are ways, let's see if that question gets answered as we go through the tutorial. All right, so I'm going to split my screen here, and I'm not seeing my shell window now. Where did that go? Oh. Hold on just a sec. I learned this trick from somebody, and I think it's like the most awesome thing. So the split screen mode. Okay, so just for what I've done is I've pulled up that repo that I mentioned earlier, and just in case you missed it, there's a separate branch for the ideas. This is kind of, I've given similar tutorials at SC and other venues, and I've made one sort of specifically for today. And what we're going to go through is just this. I'm going to briefly walk through this hands-on portion just to give you a feel for what Docker looks like in action. So again, if you want to default at home, what you'd want to do is install Docker on your laptop or workstation. If there's some challenges to doing that, you can also, there's something out there called Play with Docker, and you can log in and use that as well. But you'd ultimately want to really put it on some system that you have, you know, continuous access to. All right, so we're going to start by just pulling an image. So this gives you an idea of how you can start to work. So in this case, we're going to pull down an Ubuntu 14.04, sort of a classic version. I've actually pulled this before, so it kind of quickly checked and said, oh, this is, you've already got it and it's up to date. If I was pulling something fresh, or if you did this at home, you may see it start to pull down individual layers, and it might take a little bit longer to get finished. All right, so the image is now on my system. I'm going to, just to show this, I'm going to do Docker images to list it, and you can see there it is at the top. I've got a lot of variants and stuff on my laptop as well. Okay, so we pulled an image down. Now let's try to do something with it. So we're going to start by using Docker run. This is actually to kind of consume that image and use it as a container. And we're going to pass a couple of flags to it. So -it means interactive and terminal. So we want to tell it we're going to be interactive in this session and do a sudo terminal. And then the other one I'm going to do is --rm. Docker will actually, when you create a container, it can keep the remnants of it around, and you can actually use it to create other images. But in this case, we don't really want to do that. And so I'm going to just tell it to, after I exit, just let go of that thing and clean it up. And then we specify the image we want to use. All right. I'm going to do that. And here we are. Now I'm at a shell. And a few things you'll sort of notice right away is, one, you'll see that I'm root in this. This is kind of a default behavior for most containers. There's ways to, or images. You can override that, but you'll notice typically by default you're root. And you can think about, we'll talk about some of the ramifications for that in HPC environments a little bit later. But, you know, here I am on my Mac, and I'm in this Docker image, and, you know, I'm in an Ubuntu 14.04 environment. So, you know, all the things that you would expect to see in Ubuntu are there, and I can install tools, do whatever I would normally do in Ubuntu, and it'll behave that way. All right, so, you know, that's just a quick pulling the image down and going into it. Now, you know, oftentimes we don't want to just take a very stock base OS like Ubuntu and try to use it from scratch. We really want to start to customize it. So let's talk a little bit about how we can go about doing that. So I'm going to go, this is a checkout of that repo that's shown on the left here. And we're going to follow this next set of operations. We're going to create a Docker image of our own. And I've already started this. I've already created the directory, and I just CD'd into it. One thing to note, when you're creating Docker images, you'll want to kind of put those in a separate directory, because what the Docker build tool does is it'll kind of take a snapshot of the full contents of the directory you're in and kind of make that available to the build environment so that it can pick things out of there. And so if you're in like your home directory and you try to do this, you'll see it trying to kind of send this huge bundle of information that's not going to necessarily be put in the image, but it's trying to make it available for the build process. So, you know, the short thing is make a directory, CD into it before you start this. And then we're going to create two files in this case. We're going to create one called script, which I've already done here. It's just a simple bash script. So nothing fancy there. And then we're going to create a Dockerfile. And you can think of a Dockerfile as just like a recipe for how to create these images, right? And there are different ways you can build images, but this is by far the kind of recommended approach. And the reason is because I can look at this Dockerfile, you know, a year from now, or somebody else can look at it, and they can very clearly see, like, okay, this is what was done to create that environment. Whereas some of the other techniques, there might be a lot of information that's kind of hidden that just came from, say, the system that it was built on. So in this case, we're going to use this Dockerfile to build it. there's sort of four things that we're showing off in this, four kind of instructions. There are more supported in the Dockerfile syntax, but these will get you quite a long way. So we'll go through each of these. So first off, you see is there's this from part. That's basically saying, like, what do I want to start with? What's the base kind of layer that I want to begin with? And so you're generally not going to start from a blank page. You're going to use one of the kind of standard OS images that are out there. So that could be Ubuntu, or it could be CentOS, OpenSUSE, and there's other variants of Linux that are really been tuned for container environments that could potentially be used as well. All right. So in this case, we're going to use Ubuntu. The next is label. So this is really just a way to put metadata and associate it with this image. And one standard convention is that you typically would use, you would specify who the person was that built it. And the way this is done these days is through this label in a standard label called maintainer. All right, so I've done that. Next is add and run. And these are really the heart of how you build images. And so what add means is it's saying, take something from what's happening when the build process happens, is it creates this container and it's kind of transforming it and modifying it, and then eventually it'll basically commit that and you can save it, right? So, but you need to have ways to get information into that container environment. So add does that action. So it basically says take something from out of the container environment and put it into the container environment that we're building. So here we're saying add the script that we just edited earlier and locate it in /bin/script. And then in the next step, we're using run. So this basically is telling the Docker build to do this operation inside the container environment. So in this case, we're just going to move that script into bin hello, and we're going to make it executable. All right. So this is kind of a silly way to do it. We could have just as easily put it directly as bin hello and just made it executable. But this is just to show you kind of the two, some of the primitive operations you can do in a Docker file. All right, so now we're going to build that image. And so I'm going to use Docker build to do that. And then there's just a few parameters we need to pass. One is this -t flag, which basically says, what do we want to call this or label it? So it means tag. So for our example, we're just going to call it hello 1.0. And so that's a way for me to reference it later on. And then very easy to overlook, but you need to tell it like where to start the build from. So usually you just do this from the working directory that you're in, but you could give it a different path as well. So I'm just going to say dot to say the current working directory. All right, and there it's built it. Now you'll notice in this case it says cached, cached. I've built this earlier, and Docker, the Docker build tool, is actually pretty intelligent, and it can detect when something has changed or not, and it's sort of like a makefile. It'll follow from that point on. We'll talk a little bit about the ramifications of that later. So you can see it went through and ran all these steps to build the image, and it's saying it was successful, and it's tagged it as hello. So now if I do if I list it, you'll see it in there somewhere. It's right. It's this line right here. All right. So my image has been built. And now let's do sort of like we did before with the Ubuntu image. Let's try running it. So we're going to do Docker run. Again, interactive, remove after we're done. And we're going to do 1.0. All right. And so here I'm, again, back in that environment, but I'm going to try running hello, and yep, it works. So, that's a command that wouldn't normally be part of Ubuntu, for example. We've added it now to our customized image. All right. So you can run things interactively. You can also just run it directly from the run command. So I can pin that to the end, and it'll run it directly and then exit too. Right. So you don't have to do all these things interactively, of course. And there are other ways that I'm not going to go in today, but you can even tell it that what to do by default if you don't specify any additional arguments. So we could set it up where it would actually run hello by default and, without any additional input too. All right. Lastly, let's go through, here we're just able to use this on our laptop, but what if we want to use this on other systems, or we want to share it with people. I mean, this Hello app is pretty awesome, so I would really like to share it with the world. So what I'm going to do is I'm going to tag it. The thing is here what we're going to do is we're going to push it to Docker Hub. So it's kind of like, again, Docker Hub is a little bit like GitHub. It's a place where you can push images to, and then other people can pull them down. And you can have public images and private images, similar to how you can have public and private repos in GitHub. So we're going to push it, but before we can do that, we really need to tell it what name or organizational space to put this in. And so we're going to re-tag the image, and this time I'm going to put my Docker Hub username in front of it, so scannon, and then the name of whatever we were going to call it. So we're going to keep the same name, Hello 1.0. All right, so that's real quick. That hasn't done anything yet. All it's done is tag the image, and if I look for, you'll see there it is, right, and 14 days ago. Right. So now it's tagged, and now I can actually do the push. Now, in order to do this push, I've already done some things earlier. I'll just quickly show you for those that want to try this at home. Not seeing the. I'm not seeing my. Let's see if that does it. There we go. You'll need to go to Docker Hub and create an account on Docker Hub, and then you'll also need to log in on your system. So you'll do a Docker login, and then it'll prompt you for username and password, and then you can log in. So I don't know why it's not actually searching. All right, I'm not going to bother with this for now since I'm having problems with it. But just again, you'll need to go to Docker Hub and sign up for an account, log in through the Docker tool, and after you've done that, then you can use Docker Push to push that image up to Docker Hub. So we'll do that, and you can see it's pushing each of sort of the components of this. You also start to see some of the power in this, the way Docker structures these images. It recognized that some of this already came from the Ubuntu image, so it didn't need to push those contents again because it already has it in Docker Hub. So it really only had to push the things that were kind of customized or different about this image. All right, so we've gone through that. How are we doing on time? I think we're doing pretty good. I'm going to quickly show also a little something slightly more advanced. This is when we do this in live with people in the room, we usually do this as a hands-on portion and let them try it on their own. I'm going to just run through it though, just so you can see what it looks like. And let's see, yeah. All right. So we'll talk about running MPI applications in as containers a little bit later. But here's a simple one that we're going to do first. So let's see if we can run an MPI application on our laptop. So here we've created a basic Hello World app MPI application. The code for that's in the tutorial material. So if you just want to cut and paste it, you can do that. You don't have to start from scratch. And then we need to create a Dockerfile to build this. All right. So to kind of make this a little bit easier, there's a base image. Rather than starting with just Ubuntu, we have a base image that we've already installed compilers and impitch in, and I've pushed that up into a nurse namespace. So we're going to use that as a starting point just to make things a little bit easier. All right. Like before, we're going to add the contents of that directory into app. So we're not going to add just one file. We're going to add just go ahead and get the full contents of that and put in the app directory. And then our run command, we're going to cd into that directory, and then we're going to use the MPI compiler wrappers to compile the application and call it app hello. All right. So fairly straightforward. Now let's go through that same process again. This time I'm going to go ahead and put my Docker Hub username in front of it at the start. And we're going to give it a tag name, and we're going to build it. Again, I've already done this earlier, so it was super fast. Also, if you did this at home and you started to pull this, it would have to pull that image first. Oops, let me repeat that. But it's not a huge image. It should pull down pretty quickly if you're on a decent network. All right, so we've built that. Let's try running it now. We're going to do the same way before. What did I do? Oh, man, 2 misspellings in the line. All right.
Hey,
now,
can I interrupt for 1 second?
Yep.
So we have a question. I think it could now
Clarify.
might be a good time to ask.
Okay.
So the first question is, so the purpose of a container is to create some virtual machines on the laptop for development, and are you using LXC?
Okay. So so let me clarify that it winds up that on a Mac, it does run a virtual machine kind of behind the scenes for you. But when you install the Docker tool, it basically does all that for you, and you don't actually manually configure any virtual machines. It's all abstracted and hidden from you. And then the Docker command tools that you use to interact with Docker are natively installed in the Mac environment. And the Windows system works similarly. If you were on an actual Linux system, say your laptop or your workstation was an actual Linux system, you would just install Docker and there would be no virtual machines in that case. And in here, in the examples we're doing, we're using it for development, but you can really think about this as it's a way to wrap your application, package up your application so that it's easily, everything that you need to run it is self-contained, and then that means you can go and take that elsewhere and run it. So when I build these things, I'm not relying on the fact that there's other software installed on my laptop to make those things work, right? Everything's defined inside that Docker image. And when I take that to an HPC system, same thing. So it wouldn't matter if libfoo was not installed on that system. It's going to come from the Docker image, and that library would be inside the Docker environment, right? So things are much more portable and self-contained.
Thank you. And I think this may be a longer question for you, but so we can keep going and come back to this. But somebody is also asking, how are compiler versions being handled? Yeah, because that can be a problem.
Yeah. So the main thing you can think of is you control this environment that you're defining, right? So if you need a specific compiler version for your tools, or a specific library version, then you would just install those. You would install those tools in your Docker image, and you'd pick the versions that work for you. So it wouldn't matter if take my image to NERSC, and NERSC has upgraded compilers from this to that and libraries from this version to that other version. It doesn't matter because all of that's coming from inside my image. There are some very specific exceptions to that I'll talk a little bit about later, but in general, that's the rule. And so this is the flexibility of it. You can really tailor this environment to exactly what you need for your application, and you can maintain that same image and run it later on, and nothing's going to change. It's going to keep running the way it was. And when you're ready for to do an update and you want to use a different compiler, you can create a new image, put the new compilers in there, put new libraries in there, build that, test it separately while the other one's still the same as it was, and then start using the new one. All right. Whoops. All right. So just to finish off this example, were there any other questions, Ashley?
No, I think, well, can you change 2 tools from different containers to process data in a row?
You can. So this is just to show quickly. Here it is running. I can also do an MPI run. Okay, there. All right. So yes, you can chain different containers together. So I could have one image that has tool foo in it and another image that has tool bar in it, and you can pipe from one Docker run to another. So that works. You can also there's ways to mount in file systems that I'll talk about later, so that you could have a file system that that kind of lives outside of the container environment that you could use between those execution steps, right? In general, if you're building a pipeline, I recommend trying to put as much of that into one single image as possible. Even if it makes the image a little bit larger, it kind of gives you one self-contained way to run that pipeline. But I know there may be some cases where, you know, you have tool 1 is incompatible with tool 2 in the same environment, so you really want to have those as separate images. All right, so that's the hands-on portion, at least for this step. Let's go back to the PowerPoint, and I'm going to kind of continue on and now start to talk a little bit about containers more in an HPC context. So up to this point, everything I've done, I've just done on my laptop. So I did an MPI run, but you know, it's only going to be limited to the capability of my laptop, obviously. So I can put in a large number there, but that doesn't mean it's going to run much faster. And I'm limited to the memory and other resources that are available on my laptop. So let's talk a little bit about, you know, what it means to run these in HPC environments. Okay, so first, I know that there's a lot of people on this session that maybe are not intimately familiar with some of the DOE facilities and systems. So just briefly, NERSC is the kind of production office computing facility for the DOE Office of Science. So we really provide computational resources for the full breadth of research that goes on within the Office of Science. And we have, that number is actually low, I meant to update it. We have something in the neighborhood of like 7,000 users and, you know, 750, 800 projects that are active right now. And in the past, you know, traditionally, NERSC has really been focused on kind of modeling and simulation workloads, but increasingly we have users that are coming to do more data-intensive type applications. So data analysis, you know, experimental and observational data analysis, or other kind of big forms of big data analytics. And then, you know, more recently, a lot more machine learning. So this creates a challenge for us because we need to support all this breadth of applications on our systems, and it's hard to keep up with it. And so one way we can potentially do that is to use containers. So we just have been playing with Docker and saw how cool it is. Why don't we just run Docker on the systems? Okay, so there's a couple of reasons, but the real big ones are these first 2 or 3. So the biggest one off the bat is this the security model in Docker. So if you have the ability to run Docker on a system, you kind of, as it exists today, you effectively kind of have root access on that system as well. So here I show a simple way to kind of demonstrate that. We didn't use it yet, but I alluded to it, you can do volume mount. So you can take something from outside the container environment and map it into the container environment. So in this example, I'm going to take / the root directory, and just mount it in as /mount. Now, all of a sudden, inside that container environment, I have access to the host system's file system, and I could go and start to modify things, right? So clearly on a shared resource like we run here at NERSC, this would be a non-starter because we have, like I said, thousands of users, and that means they could modify the system, but it also means they could access other people's data or modify other people's data. So this is like the #1 reason that we needed some other approach. There are other things like Docker, as it's typically run, kind of uses and assumes local disk, and our systems don't always have that. In other words, we really needed to integrate with the resource managers that we run on the system. So for example, here at NERSC, we run Slurm, and we really want Slurm to be the one that's partitioning up resources. And then there are other things that also introduce challenges. System requirements when it's not as big of a deal as it used to be, but you know, there's other aspects of integration that can be challenging. So because of those challenges, that led us to develop Shifter. So this is one example of an HPC runtime. When we were designing it, we had a couple of goals. One is we wanted users to be able to kind of use the Docker ecosystem, be able to run, you know, any image of their choice, and not require any system administration intervention. So we didn't want it to be like, yo, you've got to go get some approval from somebody in order to do this. We wanted it to be seamless. We want them to still be able to access their file systems and the network without any overhead. And like I said, we want them to still be able to use this Docker ecosystem. So there's thousands of images. I mean, there's more than that. There's a ridiculous number of images in Docker Hub. And we want them to be able to just easily take advantage of those. And we want it to be as seamless as possible, but we also want it to be robust and secure and performant. So we want it to really perform well on our systems, even at scale. So the repo for Shifter is there. And I'll talk about some of the other HPC runtimes that are also out there. Shifter was one, I think it was really the first HPC runtime, but more have appeared on the market since then. This is just briefly sort of the components of Shifter. I won't go into too much detail, but really it boils down to what happens when you use an image in Shifter. There's a gateway piece that'll take that image and pull the pieces down and then kind of repackage it in a way that's efficient for the HPC system. There's a runtime component that's out on all the compute nodes and login nodes so that the users can then execute and create these isolated environments from the image. And then there's optionally this workload manager integration component. So for example, at NERSC, we have it integrated with Slurm. That makes it a little bit easier to use these with the batch scheduler and also a little more performant and scalable. All right, and just to show you what it looks like to use Shifter, it kind of mirrors the Docker experience with some syntax changes. So a user that wants to pull an image down would, instead of doing a Docker pull, they'll do a Shifter IMG pull, and then they specify the image just like they did before. But you only need to do that once on the system. What that's going to do is, like I said, it's going to pull those pieces down and convert it and get it ready for use on the platform across any of the compute nodes at that point. So you don't have to do this individually on each node. You just do it once on the system. And then to run in that container environment, you just use the Shifter tool and you specify what image you want in the command. So in this case, we're going to do, again, use the Ubuntu 14.04 image, say bash to go into an interactive shell. And just to show that we're in that, we're going to do an LSB release. So, you can see it's fairly easy. If we have time at the end, I'll maybe do some quick demos just to show a little more of it in action. So, here we're doing Ubuntu, but this could easily be an image that has some scientific toolchain installed in it or some application. And so rather than me having to figure out how to build it from scratch on the system, I can just go pull that down and start using it. Or if I'm part of a larger collaboration, one person can build that image, push it to our repository, and everybody else can start making use of it. When we originally were developing Shifter, it was really about productivity. We wanted to make it easy for people to kind of get their applications running on HPC systems, which maybe they weren't used to running on. But we also found some other performance benefits as well. And so this is a very specific one around Python applications are kind of notorious for not running very well on, especially at scale on HPC systems. And so here, this is a benchmark that sort of simulates or emulates a Python application that's maybe very complicated and loads lots of libraries. And we've run it at 4,800 MPI range. So not super large, but not tiny either. And then the measurements here are on different file systems at NERSC that have sort of different characteristics. Scratch is a very fast local Lustre file system on the systems. So it's fast, but it's not necessarily fast at hosting Python applications. Project is a GPFS file system. DataWarp is a solid state storage-based file system, a flash-based file system. And then the other Common is one that's really tuned for software. And you can see Shifter all the way over to the right. So in this graph, lower is better. So you can see that Shifter is providing sort of the best-in-class performance. So in general, when we have people come to us and they're trying to run, especially Python applications or some other types of applications that have a lot of libraries associated with them, they're trying to run those at scale, we'll recommend that they consider making a Docker image out of that and use Shifter to run it. And I'll give an example of another application that's used Shifter to the same kind of effect, but not a benchmark. Another, kind of question that people often wonder is like, well, and we started to explore this a little bit in the demo earlier. What can I use, Shifter or these container runtimes to run MPI applications? And the short answer is yes, but how you go about doing it, there's a couple of different approaches. So the challenge here is it's easy to put MPI into your container build environment. We did that earlier. But the real question is, like, if I go run on a system that has a special interconnect on it, say InfiniBand, or in the case of a Cray, maybe something like the Aries network, I want to make sure that I get the right set of libraries that are compatible with that network. All right. So one way would be like, I just go and collect those and I put them directly in the image. So if I go inside that image, I would see, open, InfiniBand fabric optimized libraries. That works, that's nice, but then it's not very portable. I can only run it on systems that have that network, all right? Kind of an extension of that would be the site, like Nurse could provide a base image that has those libraries directly baked into it. And then you could build images that are sort of based off of that. So this is nice because it takes a little more of the work out of the user's hands. They're not having to do quite as much, but they still have this, it's not as portable, and they still have to worry about rebuilding it if something changes. The last one that's got the box around it, this is the model that we're actually advocating for and most users are using here. We actually, Shifter will automatically, will take advantage of the application binary interface compatibility in something like MPitch. And so you build your image with a stock MPitch implementation, and then what happens is when you run that with Shifter on an HPC system, it can dynamically bring in the libraries and make them available inside that container environment. And then it'll modify the loader to load those by default instead of the ones that are in the image that aren't optimized for the interconnect. So, at a little loss of reproducibility, because there is some stuff that's kind of leaking in from the outside, you get something that's more portable and you still get the full performance benefits of running on a system. So we've used this approach. There have been studies done where they've done benchmarking using this approach, and basically they see as good a performance running in a container environment, in some cases even better. I think in one rare case we saw something that was slower, but I think we tracked it down to something, some other artifact. So this is just an illustration of using that approach. Here we have our Docker image. In fact, this is the same one we just went through in that exercise. You build it just the way I did earlier, and then the only difference is when we go to run this on the system using Shifter, you'll see we've we're taking advantage of the Slurm integration with Shifter, so that in the batch submission we can actually tell it what image to use. And then we do a normal S run, so those familiar with Slurm will recognize this. The only difference is we just have Shifter sort of there in the middle before we run the application. So everything kind of looks like it normally would with just this one extra kind of change. And that would then run, and then what happens at runtime is the libraries for the Cray system would automatically get mapped in, or if we were running on an InfiniBand cluster, the libraries for the InfiniBand network would get mapped in, and those would get used by the application. And this all assumes the application was dynamically compiled or dynamically linked. So that's just a little bit about how Shifter can run an MPI. All right, so let me talk. There are some slight differences. I think I'll just go through this pretty quickly. The big differences between using Shifter and like stock Docker is, one, the images are mounted up read-only. So if you try to modify the image at runtime, it won't work with Shifter. There are ways to work around it, but this is something that people can get snagged on. The other thing we showed earlier, by default, oftentimes in these containers you're running as root, and in Shifter you're running as yourself. So this is a key security approach that we use to make it secure. And there's some others as well, but I won't go into those in detail. I wanted to quickly talk about some of the other HPC container solutions that are out there. By far the one that's probably most popular and maybe you've heard of is Singularity. So this was, incidentally, was also developed at Berkeley Lab, but it was developed in the IT department here. And since that time, there's actually been a company formed called Scilabs that's kind of spun off and continuing development of it and support. And so you can actually get support contracts for this. It uses some similar models to Shifter and how it does things, but there are some differences as well. It's generally a little bit easier to install than Shifter, and I think that's one reason it's become so popular. It also has a native image format that it supports in addition to Docker. And in general, some people may like that. I would typically suggest using the Docker image first, and then you can convert it to that format and use that where it makes sense. And then another one that's a little more recent called Charliecloud. This one's interesting because it's very lightweight. You don't even need, if the system you're running on supports certain features, which most do now, you can actually install this as a regular user without any intervention from the system staff and start using Docker images. So that's pretty cool. The only deficiency to it is it doesn't do some of the same techniques Shifter and Singularity do and how they package and mount the images up, so it's not going to scale quite as well as Singularity and Shifter can. And just to show some examples, I'm actually going to not spend time on this. Is just an example of what a Singularity recipe looks like. This is kind of their equivalent of a Dockerfile. If you've ever done RPM builds, it's got a lot of kind of similarities to that. It's kind of inspiration from it. And there's an example of how you would build it. More interestingly, this is sort of some examples of what it looks like to run and use an image using Singularity. And again, you'll see the syntax is very similar to kind of Docker and Shifter in certain ways. So here we're pulling an image, a Docker image down, and we're going to create this local version of it called myimage.simage. That's their native format. And then once we've done that, we can use that image similar to how we did before. So you can run it interactively in a shell, or you can run kind of the default settings for it with the run command. You can also you can skip the pull, I think, and you can also just tell it to use it directly, and it'll sort of do them in one combined step. And then Charliecloud, the way you would normally use it is like you would start by, on a system where Docker is present, you use some tools to take and extract that image into a tarball effectively, and then you can copy that over to another system, the HPC system, and then you can use tools to then unpack that and then use Charliecloud to run that unpacked image. So, similar kind of construct, a little bit different in how, right now today, it can't directly pull from something like Docker Hub. So you would do that on your laptop and sort of move the image around. All right, doing decent on time. I'm going to talk a little bit about some other tips and tricks. Are there any questions we need to?
Hey Shane, I've had this one come up 3 times, so I probably should clarify. So I've had some questions about what scheduler systems does Shifter and Docker work with in terms of, is it just Slurm, or does it work with all scheduling systems? Okay, so it's probably worth clarifying. So with Shifter, we have integration with Slurm, and we've also in the past done Torque Moab and UGE. Those are optional pieces. You don't have to have that in order to use them. So you can always just, in your job, instead of, you just append Shifter to your job script, so if you're running the application, you would say Shifter -- image name application, and you would just put that directly in your submission script. Similar approach for Singularity and Charliecloud. So the batch integration is kind of an optional component. For Shifter, where it's useful is what it does behind the scenes if you use that integration is it'll kind of pre-prepare the environment across all the compute nodes. So when you go to launch your application, everything's kind of ready to go, and it'll use that pre-prepared area to start things up. So it can be, it generally scales a little bit better than just kind of running it directly from the command line. But that's kind of an optional integration piece. So there are definitely some other questions, but I think a lot of them are kind of longer in nature. So if you want to go through this part, I would say keep going.
Okay, that sounds good. All right, so I alluded to volume mounts earlier when I talked about some of the security issues. That capability is there for good reason. So what it allows you to do is take data take file systems from outside the container environment and make them available inside the container environment. So this is oftentimes the way you're going to do, if you're doing some kind of data processing pipeline, you don't want to put all your data that you're processing directly in that image. You want to have your tools in the image, and then you want to bring in the data as needed for the analysis. So the volume mounts is really useful for this. And what's nice about it is you can control where that shows up inside your container environment. So you could, for example, always map data so that it's in the /input directory, and your tool will just look for it there. And so then as you start to move between different systems, you can kind of hide that aspect from the image itself and just map in the right paths into the right locations. So this can be, is a useful feature. And all the container runtimes support this in some way, shape, or form. And so this is just a simple example. So here I've got a scratch directory on Corey. There's a directory called My Job in there that's got some stuff in it. And then when I run the shift command, the only thing that's different, I'm adding this -- volume, and I'm going to say take the scratch My Job directory and map it to /data inside the container environment. So now I'm inside the container environment, and if I do an ls of the data directory, I see the same contents. And if I wrote information into that, it would get modified, and it would be available in the same location. So there was this question about running multiple tools. This is kind of the typical way you would do it. You might have sort of this processing directory that you mount into your different container executions, and they could each see that and operate on it. So they could operate it in sort of subsequent steps, like in a pipeline fashion. There's a feature specific to Shifter. I don't think the other ones have a counterpoint to this. This is something we added to Shifter because we saw cases where, like I mentioned, the Cray systems don't have local disk, and there's certain applications that are really just designed and sort of assume that, right? So what this does is we use some of the same techniques we're using for the images. We create on each node, you can create a writable area, and that gets mounted and mapped in just at runtime, and it's an ephemeral path, right? So after I exit out of the container, it actually goes away and disappears. So this is really useful for cases where you have applications that maybe need some local kind of scratch space. Maybe they're doing a lot of transactional I/O. In general, we see very good performance in those cases. So we've used this, for example, to run Spark at larger scales on our Cray systems. And this is just an example of doing that. The one thing to remember here is this is an ephemeral area. So once I exit out, if I try to go back in, that's lost. So you wouldn't want to put persistent information here. Or if you did, you'd want to make sure that you copy it out before you exit it. All right, now I just want to talk a little bit about some best practices when you're creating images. All right, so one is how these layers get created. So you can do a series of run operations, but each of those results in what's called a layer and a Docker image. So you can think about it as whatever is changed in that operation gets bundled up and stored, right? And then an image is just a collection of all of those tarballs, and it unpacks those in a sequence, right? So the problem with this first one is, if you think about what's happening is you grab this image from, over the web, and it gets stored in a layer in the image. And then you unpack that, and there's a new layer that has the unpacked contents of that tarball. And then you have another layer that is the compiled and installed information for that application. And then that last one, actually what gets saved in the Docker image is it says, hide these other places from the layers above, right? So it's kind of like masking them out so that they don't show up in the image that you actually run. So when you go to build that and ship it, it actually winds up shipping a lot of information because all of those layers still get sent, even though they're ultimately hidden. So in the second version, what we're doing is we're doing the same operations, but we're doing them all as part of one layer. And so since it only looks at the final product of that layer, this is going to be a lot smaller. All you're really going to have is just the installed application. So in general, you want to follow that kind of technique. And when you do that, you want to make sure of, you'll notice that I'm using this ampersand model. This is just a general shell trick, and it's probably a good one to use in other places as well. So with a semicolon, it means run this, I don't care what happens, do the next step, do the next step. So let's say in that process, the make failed in some way, right? It's going to keep chugging along, and the layer, Docker will think of it as if that all succeeded, even if it didn't. In the good example, what we're doing is we're chaining them together. So if at any point in that sequence something fails, Docker will detect it, and it'll stop the build at that point, right? So again, this is not specific to Docker, but it's something that it's a trick you wind up using in Docker files pretty frequently, at least I do. And then the last is of these is how the ordering really matters. So I mentioned that Docker's, we saw in those examples how it cached things, right? So it's kind of like making that it can detect if something's changed or needs to be done. What triggers that typically is, one, either a change in the Docker file itself. So if I change something in the Docker file, any steps from that point and below, it'll redo, right? So that's one way. Another one, though, is when we're adding stuff. So it'll actually create a fingerprint of the contents during the build for whatever you're adding. And if it detects a change, it'll redo that and do any steps afterwards. So the problem with the first one is if I even make a small modification in that directory, it's going to wind up rerunning all these apt-get steps. And those could take a long time, right? So better to put those up front. And then that way, as I make source code changes, it's not going to reinstall my GCC every time I do a Docker build. And in general, what you want to do is the slow changing dependency sort of pieces, put those at the top of your Docker file. The rapidly changing things, the things that you're iterating on the most, put those towards the bottom, and you'll get the best results. And there's another feature that Docker added a few years ago called multistage builds. This is useful for cases where, like, the problem with some of these, like if we're installing GCC so we can compile our application, it's winding up in the image itself that we use for running it as well. But we don't really need GCC to run our image. We just need it to prepare it, right? So multi-stage builds is a way to kind of address that. What it does is allows you to kind of have multiple image builds, and then you can actually grab stuff from one image build and pull it into another as you're doing the build process. So this is just a very toy example of that. Here we're we're doing this from, but we've added this extra label as build, right? The other steps look the same. We're going to install GCC, we're going to bring in our code, we're going to compile it. And then you'll say, oh, look, here's another from line. So now we're going to start over, but we're going to actually copy this artifact, this code build from other image and bring it into the one that we're building. So the nice thing about this is this image would have our code in it, but it wouldn't need to have GCC installed in it, right? And this is really important if you have things that are very complex application builds that maybe have lots of libraries and tools that you need to do it. All right. Lastly, just in general, here's some other tricks. You want to avoid using really large images because it takes a long time to push those to Docker Hub or even pull down to use for Shifter. So in general, what you want to do is just have your applications and tools in the image, and then use the volume mounts and, as I say, Scratch, use whatever disk, fast disk is available in the system to store your actual large data and the pieces that maybe are going to be processed. You can also use this approach for when you're using, for doing sort of ongoing development and prototyping. So you can kind of have some things that you keep outside of the image as you change them. That way you don't have to keep rebuilding the image to test it out. And then once you kind of know that things are working, you can put those pieces back into the image build process and actually bake them into the image. And getting towards the hour here, this is just an example of real world example of somebody that used Shifter and Docker images to solve a science problem. And so in this case, what they're doing is simulating cosmic microwave background radiation for a next generation telescope. And they needed to run all these different instances, and they actually wanted to run at the full scale of the Cori Phase 2 system. So this is Knights Landing nodes, Xeon Phi nodes, and there's like 9,600 of them in the system, so it's something like 600,000 cores. And when you tried to do this without Shifter, it basically, because of that Python behavior that I talked about earlier, he was hitting, it was taking him hours just to start up his application. He actually wasn't getting any science done because it was just still trying to start up the application. So he put that all into a Shifter image and then took advantage of that performance benefit that I talked about earlier, and he was able to run at the full scale of Cori KNL nodes. And and he has this artifact that he can go back and reuse, in the future as well. So here it was really key to them actually accomplishing their science goals. It wasn't just a productivity play. It was really a make or break thing for them. All right. So in summary, hopefully I've convinced you that containers are awesome and you should start using them. Again, where I think you'll see the gains are this productivity aspect, because you'll have so much better control of your applications, being able to what you can use for your environment. Things will be more portable. You can build stuff on your laptop and run them on another system, assuming that they're architecturally compatible. You can share these with your collaborators. You can easily rerun them, down the road and not worry about things kind of suddenly breaking on you. And you actually, in many cases, you actually see some speed ups. So again, here's some resources. There's the repo itself. We'll be answering questions, of course. I'll try to get through those as quickly as I can. And there's other resources and material out there. So I just invite you to Google things in most cases. I didn't put references for Singularity or Charliecloud, but if you Google those, you'll find a lot of training material for those as well. All right, and we've answered some questions, but I can take a few more before I have to disappear. No.
Okay, so Shane, then let's see here. For those of you who are willing to stick with us a couple of minutes here.
Should we open up the